Good morning students. Happy to meet you all once again through this video lesson. What is your aim in life? Do you want to achieve something great? Do you have the confidence and courage to move towards it? The Bible says in Philippians 4:13, I can do all things through Christ who strengthens me. So make God your partner who gives you the strength, wisdom and knowledge from above, and plan big, for nothing is impossible with God. Let's move on to today's lesson, periodic classification of elements. Good morning friends. In the last class, we learnt about periodicity of properties, atomic radius, variation of atomic radius in groups and periods. We also learnt about Slatter's rule and how to calculate the effective nuclear charge using Slatter's rule. I am anxious to see what we are going to learn today. Come, let's go watch the video lesson. Ionic radius, so this is an anion and this is a cation. It is defined as the distance from the center of the nucleus till the point where it has influence on the electron cloud. So it is defined as a distance from the center of the nucleus till the point where it has influence on the electron cloud. This is an anion and this is a cation. So just understand, cations are always smaller in size than the anion. Now Pauling suggested a method to calculate ionic radius. He assumed that both the ions are perfect spheres and that they are in contact with each other, because we know there is a strong electrostatic force of attraction between the cation and the anion. Supposing this is my cation and this is my anion, the interionic distance is given by D, and Pauling gave the formula that D is equal to Rc plus Ra minus, where D is the distance between the center of the nucleus of the cation and the anion, between C plus and A minus, and Rc plus is the radius of the cation and Ra minus is the radius of the anion. Now he assumed for ions which have noble gas configuration, the radius is inversely proportional to the effective nuclear charge. I have two examples, sodium fluoride and potassium chloride. Sodium and fluoride have neon type configuration having 10 electrons. Chloride and potassium have 18 electrons having argon type configuration. So for such ions, he said the radius is inversely proportional to effective nuclear charge. So R of either the cation or the anion is inversely proportional to the nuclear charge. This effective nuclear charge ZF is given by the formula Z minus S, where Z is the atomic number and S is the screening constant. Now dividing equation 1 by 2, we get Rc plus by Ra minus is equal to Zf of A minus by Zf of C plus. If any three quantities are known, we can calculate the radius of the unknown radius of any ion. Now this ionic radius is also a periodic property. As you can see, when we go down the group, it increases and decreases across the period. Now we are going to compare the radii, ionic radii with atomic radii of both cation and anion. Now these are atoms of the alkali metals and these are monopositive cations. As it is evident, the cation size are smaller than the anion. The monopositive ions are smaller than the atoms. The dipositive ions are still more smaller than the monopositive ion, and the trivalent tripositive aluminum atom is still smaller. So as the number of positive charges increases, the size of the cation decreases, because the nuclear charge is more and number of electrons is less. Effective screening, more attraction takes place, and therefore this contraction in the size. But in the case of anion, you can see these are the atoms and these are the ions, univalent negative ions. The size is bigger here. The atomic number, positive charges are lesser than the negative charges. What happens? There are two positive ions, the size still more increases. So these are all mono or univalent negative ions. They are divalent negative ions. The size increases. Here the number of protons is lesser than the number of electrons. So effective nuclear charge attraction is less. Therefore size increases. So always remember, cations are bigger in size, smaller in size than the anions because of greater attraction and greater nuclear charge. Let us compare the size of the isoelectric ions. First, what are isoelectric ions? The ions having same number of electrons or having noble gas configuration is called as isoelectronic ions. So here we have potassium ion and chloride ion. Chloride ion also has got 18 electrons, and potassium ion also has got what? 18 electrons. Let us understand. Atomic number of chlorine is 17, so it has got 17 electrons. Chloride ion has got 18 electrons. In the case of potassium, the atomic number is 19, which had 19 electrons, but here the potassium ion has got lost one electron to become positive, and there are 18 electrons. So here more number of positive charges, less number of electrons, therefore this contraction in size. But here 17 positive charges, 18 electrons, therefore the size increases. So always understand that cations are smaller in size. So here we have many examples. In all the cases, all of them are isoelectronic. All of them have 10 electrons in the outermost configuration. But this is noble gas neon. When compared to neon, these two anions are bigger in size, but the cations are smaller in size. So as the number of positive charges increases, the size becomes smaller. As the number of negative charges increases, the size becomes bigger. Next, we are going to see what is ionization energy. This is a very important concept. This is also a periodic property. Now, I have a atom. I am going to spend some energy to remove the valence electron. That energy which I spend to remove the valence electron is called as ionization energy. So, it is defined as the amount of energy required to remove the loosely bound electron from the valence shell. Energy which I spend to remove one electron is called as first ionization energy. So I spend some amount of energy from the gaseous atom to remove an electron to form a monopositive cation. That energy is called as the first ionization energy. This first ionization energy in the case of sodium is 494 kilojoules per mole. So we know sodium has got atomic number 11, 281 is the configuration. To remove that one electron, I need to spend an energy of 494 kilojoules to remove that electron. So the first ionization energy of sodium is nearly 494.4 kilojoules per mole. So what is second ionization energy? So we are going to study about successive ionization energy. So the minimum amount of energy required to remove an electron from an unipositive, already I have removed an electron and a positive charge is there. From that ion, I have to spend some energy to remove the electron to form a dipositive ion. That energy is called as IE2 or the second ionization energy. Now, how do this first, second and the third successive ionization energies vary? Generally, the energy keeps increasing. The second ionization energy is greater than the first. The third is greater than the second. So, the successive ionization energy are greater when compared to the previous ionization energy. Now, let us try to understand the reason for this. I have taken magnesium atom as an example. Now, this is magnesium neutral atom. We know the atomic number of magnesium is 12. So, there are 12 electrons and 12 protons in the atom. Now, this is a monopositive ion. So, I have spent some energy, removed one electron to form Mg plus ion. So, in this case, the proton is 12, electron is 11. So, what do we expect? We expect the size to be smaller than this one, as we have seen already. So, this ionization energy will be greater when compared to the atom. Now, I am going to spend some more energy to remove the second electron from the monopositive ion, definitely to form Mg2 plus ion. This IE2 is greater when compared to IE1. So, the energy which I spend here is called as IE1, this is called as IE2. So, here already there is a positive charge. As you can see, there are 12 protons, 11 electrons, it will be very tightly held. So, if I am going to remove that one electron, I need to spend more energy to remove it from the nuclear attractive force. So, IE2 or the second ionization energy is greater when compared to the first ionization energy. So, because nuclear charge increases, greater attraction, the electrons are tightly held and we need to spend more energy. So, let us see how this ionization energy varies in the periodic table. First, across the period. Across the period, when we move from left to right, ionization energy increases. Why does it? This is a very important question. Why does it increase? Valence electrons are added to the same shell. If it is K shell, electrons are added to the K shell. If it is L shell, all the electrons are added to the L shell itself. And not only the electrons, for every electron, proton number also increases inside the nucleus. Let us try to understand with these examples. This is lithium. There are 3 electrons, so 3 protons in the nucleus. This is carbon, beryllium, 4 electrons and 4 protons in the nucleus. And the electrons are added to the same L shell. This is carbon, 6 electrons and 6 protons. The 6th electron also enters which shell? K shell, L shell. And this is oxygen with atomic number 8. You can see the number of electrons are more in the L shell. And this is neon. Here also the electrons are added to the same shell. So, what happens in this case? Nuclear charge increases. So, as we move across the period, electrons are added to the same shell, nuclear charge increases. Because of increased nuclear charge, the nucleus holds the electrons tightly towards itself. So, force of electrons on the valence electron increases. Because of this, what happens? Atomic size decreases. So, when I move from lithium to neon, the atomic size decreases. Because electrons are added to the same shell, you can see the electrons are being added to the same shell, nuclear attraction is more, force of attraction increases, contraction takes place and therefore the size decreases. Now, because the electrons are very tightly held by the nucleus, I have to spend more energy to remove the electrons and therefore ionization energy increases when we move from left to right. If you remember this, we can write all the reasons. Whatever be the questions, we can compare and write the answers. Now, this is not the case in this is not the normal trend. There are some anomalies in the variation. Let us see here. So, what did we see now? When I move from lithium to neon, there should be a straight increase in the ionization energy. But if you look at the graph, this is a general trend. I expect it to be a straight line. But you can see the variation between beryllium and boron and nitrogen and oxygen. Why? Why is there a change? Why is there a shift in the ionization energy? In the case of beryllium, we know the atomic number is 4, the electronic configuration is 1s2, 2s2. That is, both the s orbitals are completely filled. They are perfectly stable. There is no need for beryllium to lose an electron. So, it is very difficult to remove an electron from beryllium. That is why I have to spend great energy. So, lot of energy is needed to remove one electron from beryllium. But in the case of boron, the atomic number is 5. This is electronic configuration 1s2, 2s2, 2p1. If I remove this one electron, boron is going to be stable. So, even if I spend very less energy, normal energy, you have to spend very less energy to easily remove the electron from boron, and therefore, there is a dip in the from the expected level. Even very less energy is enough in the case of boron. Same way in the case of nitrogen and oxygen. Let us try to understand with the electronic configuration. We know the atomic number of nitrogen is 7. 1s2, 2s2, 2p3, exactly half filled. But in the case of oxygen, 2p4, 1 is extra. If I want to remove an electron from nitrogen, I am going to disturb the stability. So, I have to spend great energy to remove an electron in the case of nitrogen. But in the case of oxygen, if I remove one electron, it will also be exactly half filled by nitrogen, gaining more stability. Therefore, it is easy to remove an electron from oxygen, but difficult to remove an electron from nitrogen. That is why there is a difference in the ionization energies. Next, we are going to see what happens to ionization energy when we move down the group. When we move down the group, it decreases because valence electrons are added to the next higher shell, K, L, M like that. But even then, the protons are increasing. But what is happening here, this is group 1 and group 2. If you look at understand the electronic configuration, 2s1, 3s1, 4s1, 5s1, this is group 2. Electrons are added to the next higher shell. Because they are added to the next higher shell, atomic size increases. When we go down the group, the size increases. Because the size increases, the electrons are moving far away from the nucleus. Distance of the electron from the nucleus increases. If this is going to increase, force of attraction will be less. The nucleus cannot hold the outermost electrons tightly towards itself. Easy for me to remove the electrons. Therefore, ionization energy decreases. Let's try to understand this with the graph. This is the variation of ionization energy for group elements. Lithium, sodium, potassium. You can see that the curve comes downwards. It keeps on decreasing. Similarly, in the case of second group also, we can see there is a dip in the curve. The ionization energy decreases like this: beryllium, magnesium, calcium, so on. So, in general, when I go down the group, ionization energy decreases. So, in today's lesson, children, we will learn about ionic radius. We will learn about the variation of ionic radius, ionization energy, variation of ionization in the periods and in the groups, and we also saw about the comparison of the ionic radius of cation and anion and isoelectronic ions. This is a very important concept. Please revise the pages in the textbook, then take up the test. Thank you, children. Stay safe and take care.